Dear students, so in previous classes we were discussing about the canonical equation of vibration of a string of infinite length, vibration of a string of finite length, and is of semi-infinite length. Now in this class, now consider a problem. So consider an equation utt minus c square uxx ctt minus u square cxx equals f of xt. So show that the solution of this problem is unique. Utt minus c square uxx equals f of xt has a unique solution. That's our aim here. Here the condition is 0 less than x less than L, t is positive, and the initial conditions are u x0 equals f of x, u x0 equals f of x, where 0 less than x less than or equals L. Ut x0 equals g of x. Ut x0 equals g of x. Same x ranges from 0 to L. U0t equals ult equals 0 for t greater than 0. So these are the initial and boundary conditions. Then we have to show that this problem utt minus c square uxx equals f of xt has a unique solution. The uniqueness is our requirement. So how? So in order to prove the uniqueness, first we assume that there exist two solutions. Let u1 and u2 are the solutions. So assume let u1 and u2 are the two solutions of this problem. So in order to prove the uniqueness, we have to show that this u1 equals u2. So for consider v equals u1 minus u2. V equals u1 minus u2. Now to show u1 equals u2, it is enough to show that this v equals 0. Okay, we assume u1 and u2 are the solutions of this equation. Now we have to show that this u1 equals u2. That means when v equals u1 minus u2, v equals 0. Agree. So let v equals u1 minus u2, which satisfies or which is a solution of the equation. It is vtt minus c square vxx equals 0. Consider v equals u1 minus u2 is a solution of the equation, corresponding equation vtt minus c square vxx equals 0. So here what is vt? Vt is u1t minus u2t. Agreed. What is vdt? Vdt equals u1tt minus u2t. Similarly, what is vx? Vx equals u1x minus u2x. Vxx. What is vxx? Vxx equals u1xx minus u2xx. Moreover, u0t equals 0, ult equals 0. So what is v0t? V0t is again 0 and vlt is also 0 itself, according to this argument. u0t equals ult equals 0 means u1 0t and u2 0t are zeros. Moreover, u1lt and u2lt are zeros. Therefore, v0t and vlt are also 0 itself. Clear? That's immediate from the construction of this v. V is nothing but u1 minus u2. Agreed? So, vtt minus c square vxx equals 0 means this equation or equation is this is A. So, equation A reduces to what is vtt? It is u1 dt minus u2 dt. So we have u1 dt minus u2 dt, that is vtt, minus c square into, it is u1 xx minus u2 xx equals 0. So what is vx0? vx0. vx0 equals ux0 equals g of x, and here vx0 equals u1x0 minus u2x0. vx0 equals, it is u1x0 minus u2x0. When u be the solution of this one, ux0 equals, yes, ux0 equals f of x. So here u1x0 is again f of x minus u2x0 is also f of x equals 0. vx0 equals 0. What is vtx0? vtx0 means it is u1tx0 minus u2tx0. When u be the solution of the given given equation, then utx0 is g of x. So according to our assumption, u1 and u2 are the solution of the given equation. Therefore u1tx0 is g of x and u2tx0 is also g of x, means they satisfy the boundary conditions, means vtx0 is also 0 itself. So the boundary conditions are transformed into in this way. Agreed. Now we define e of t. Define a new function, that is e of t equals 1 by 2 into integral 0 to L c square vx square vx square plus vt square dx. We define a new function e of t equals half of integral 0 to L c square vx square plus vt square dx. Okay. What is dE by dt? Therefore dE by dt equals, differentiating with respect to t, dE by dt is nothing but half integral 0 to L c square, then the derivative of v square x or vx square with respect to t, it is 2 vx into vxt, 2 vxt plus derivative of vt square with respect to t, it is 2 vt into vtt dx. Okay, so e of t is defined this way. Now dE by dt is nothing but half of integral 0 to L c square 2 vx into vxt plus 2 vt into vtt dx. Okay, so that means which equals integral 0 to L, 2 and 2 cancelling each other, take 2 outside commonly, they are cancelling each other. What remains? Integral 0 to L, it is vtt vx dx, vtt vx dx plus integral 0 to L, yes, it is vtt vt dx, the second function, plus, now listen, what is the first term here? If you term by term integration, it is c square into, actually it is c square into integral 0 to L vxt or vxt dx. That is, integration is again with respect to x, so it changes as c square into vx vt from where to where? 0 to L minus integral 0 to L c square into vxx vt dx. Why? Because of integration by parts. Okay, listen, it is half of this one, 2 taken outside commonly, 2 cancelling each other, then term by term integration, that is integral 0 to L vtt dx plus remains plus integral of first part, that is integral 0 to L c square vx vxt dx. 0 to L Vx Vxt dx. Integration by parts. First function into integral of second. So it is a square in first function into integral Vxt with respect to dx. So it is Vt first function into integral of second minus integral of derivative of the first function Vx. Derivative of Vx is Vxx into integral of second. Okay. So this is integration by parts. Clear? So that equals integral 0 to L. It is Vtt Vt dx minus 0 to L c square Vxx Vt dx. So it is Vt into integral Vtt minus c square Vxx dx plus it is c square Vx. C square Vx into it is c square Vx into it is Vt of upper form, upper integration Lt minus Vt of lower integration 0. Okay. So it is integral 0 to L Vtt Vt dx minus c square Vxx Vt dx. Now, as it is associated, that is integral 0 to L Vtt minus c square Vxx dx plus c square Vx into Vt. It is Vt Lt minus Vt0t. What is Vt Lt? It is what is V u1 minus u2. So it is Vt Lt equals 0. Vt0t is also 0 itself. Okay, V0t equals 0. So what is V0t? V0t equals 0. Therefore Vt0t is again 0. Vlt equals 0. Therefore Vtlt is also 0 by these arguments. Okay, so the second term goes to 0. Now it is integral 0 also means it is integral 0 to L Vtt minus c square Vxx dx. But what is Vtt? Vtt minus c square Vxx becomes 0. Vtt minus c square Vxx equals 0. Therefore from equation A this also reduces to 0. That means dE by dt equals 0. dE by dt equals 0 means what is E? E is a constant. This E is a constant. Now we show that what is actually the value of this E. Here we obtained V is a constant. Now what is E0? Here it is defined as E of t equals half integral 0 to L c square Vx square plus Vt square dx. What is E0? E0 equals half of integral 0 to L c square Vx square plus c square Vx square plus Vt square dx. So at t equals 0, E0 means at t equals 0. That is at t equals 0, E of t. That is E0. So at t equals 0, what is Vx? At t equals 0, here Vx0 means Vx x0. What is Vx x0? Yes, it is Vx0. Vx0 is u1 x0 minus u2 x0. So Vx0 equals 0. So Vx x0 is also 0. Okay. Similarly, what is Vt? It is Vt x0. Vt x0 is again 0 itself. Vt x0 is also 0. Why? Because what is Vtx? Vt equals u1t minus u2t. So u1 t minus u2t. So ut x0 equals u of x minus u of x is 0. So Vt x0 equals 0 means Vx x0 equals 0 means Vx square equals 0. And Vt x0 equals 0 means Vt square equals 0. Therefore, the total quantity would reduce to 0 at t equals 0. Okay, that means at t equals 0, E of 0 equals 0. That means E equals 0. Okay, so E equals 0 means what is E? Half into integral c square Vx square plus Vt square dx equals 0. Agreed. Since E equals 0, this implies half of integral 0 to L c square Vx square plus Vt square dx equals 0. Agree. So that means the integrand becomes 0 means that happens only when Vx square plus Vt square equals 0. C square Vx square plus Vt square equals 0. That means Vx square plus the integrand constant equals 0. Sorry, the integrand is 0. That is Vx square plus Vt square equals 0. That means this means C square Vx square plus Vt square equals 0. That means clearly it is Vx square equals 0 and Vt square equals 0 since C is non-zero. Okay. Vx square equals 0 means Vx square equals 0 means Vx equals 0 and Vt equals 0. Means what is V? That means V is a constant. That constant is also 0. Vx equals 0, Vt equals 0 means V is a constant. Okay. V is a constant. Again, but what is Vx0? Vx0 equals 0. That is given. Vx0 equals 0 and as Vx0 equals 0 and this implies Vx equals 0, Vt equals 0, V is a constant, but it is given Vx0 equals 0. We have Vx0 equals 0. That means uv equals 0. V is a constant, that constant is also 0. What is u? V means u1 minus u2 equals 0. That means u1 equals u2. Hence, the uniqueness is preserved here. So this is the solution, or this is the solution of this problem. That is what we requires here. We have to prove that for there exists a solution for utt minus c square uxx equals f of xt, which should be unique. So first we assume there are two solutions, u1 and u2. Then finally we prove that u1 equals u2 by introducing this arbitrary function u of t. U of t is half of integral 0 to L c square vx square plus vt square dx. Okay, from there we say that e of t, e reduces to a constant, e is nothing but a constant, but that e equals 0, therefore v is a constant. That means that v is also 0, hence u1 minus u2 equals 0 means u1 equals u2, so that is the requirement. Agree? Okay. Now, consider another one. That's a simple problem. Solve ytt minus c square yxx equals 0. So ytt minus c square vxx equals 0, where x lies in between 0 and 1, 0 and 1, comma t greater than or equals 0, or t greater than 0. The initial conditions are y0t equals instead of L, here it is 1, y1t equals 0. Then yx0 equals, so first condition is yx0 equals x into 1 minus x, where x ranges from 0 to 1. Instead of L, here it is 1. X ranges from 0 to 1. And ytx0 equals 0, where again by the same range 0 less than or equals x less than equals 1. And the second condition is yx0, second one, yx0 equals 0 if 0 less than or equals x less than or equals 1, and ytx0 equals x square if 0 less than or equals x less than or equals 1. So find the solution of the given equation ytt minus c square yxx equals 0 subject to these two conditions. So the initial conditions is y0t is y1t is 0. Then there are two, subjecting the two conditions, yx0 is x1 minus x and ytx0 is 0 when x ranges from 0 to 1. Second condition is yx0 is 0 and ytx0 is x square and x ranges from 0 to 1. Then how? So we know that ytt minus c square yxx equals 0. Then according to these arguments, so it is the vibration of a string of finite length. So we know that. What is the solution? The solution is y of xt equals sigma n ranges from 1 to infinity sin n by x by L into an cos n by ct or n by c by L into t plus bn sin n by c by L into t. So this is the solution of the vibration of a string of finite length. Y square ytt minus c square yxx equals 0. Its solution is yxt equals sigma n ranges from 1 to infinity sin n pi x by L into an cos n pi c by L t plus bn sin n pi c by L t. Okay. So consider the initial condition. First case, yx0 equals x into 1 minus x and ytx0 equals 0. Here yx0, what is yx0 case first? yx0 equals 0, but yx0 means f of x. Sorry, yx0 equals not 0, yx0 equals x into 1 minus x. So this is f of x, yx0 equals f of x. And ytx0 equals 0, that 0 means ytx0 is g of x. Okay, so what is an? But we know that an equals 2 by L into, here what is L? L equals 1. 2 by L, here L equals 1. 2 by L into integral 0 to L f of x into sin n pi x by L into dx. Okay, so that equals, and what is Bn? Bn equals 2 by L into, here again L equals 1, integral 0 to L as g of x into sin n pi x by L dx. So according to the first condition, ytx0 is g of x. Ytx0 is g of x, that is 0. So the second part means bn goes to 0. Bn equals 0. So what is an there? An equals 2 into integral 0 to 1 f of x. That equals 2 into integral 0 to 1. L means 1. 0 to 1. X into 1 minus x sin n pi x by L dx. So that is nothing but 2 into integral 0 to 1 x sin n pi x by L dx minus integral 0 to 1 x square sin n pi x by L dx. This L is 1. Again L is